What's up everybody? Jacob here with Smetting Performance. This is going to be part 3 of our 1000 horsepower, 632 cubic inch naturally aspirated big block Chevy engine build. In part 1, I went over crankshaft balancing. In part 2, Shay assembled the short block. He talked about bearing clearances, ring gap, what to look for, the type of rings and components we're using. And in part 3, I'm going to talk about timing systems. So, on my right here, I have a Jessel belt drive timing system. Okay, so here's the crank sprocket, here's the cam sprocket, and they are going to be connected by this belt drive. Fairly straightforward. This is different than the normal chain-driven system that we would normally use in our big block Chevy engines. This is a 1/2 inch seamless roller single chain with steel gears. And these are extremely robust and extremely durable. I have never had one of our chain drive systems break in the 7 years I've been here and the thousands of engines I've seen go out the door. So, we are going to a belt drive not for durability, because I have full confidence that this would survive amazingly well in this application. We're going to this system for the adjustability. Okay? So what do I mean by that? This is the crank sprocket. It has a single keyway in it, and that key is going to line up on the crankshaft key. So it's indexed, it's fixed. However, the cam sprocket, if you look right here, we can adjust it. So, with this sprocket, you can loosen these 4 bolts right here, and you can advance or retard the camshaft timing in relation to the crankshaft. And what that does is we can shift the valve events and where they open in relation to the piston. So, if we get this motor on the dyno, and its peak horsepower and peak torque number are too high in the range and we're losing too much torque down low, we can simply advance the cam a couple degrees on the fly right there. Now we bring the torque curve lower, we make more average numbers, and the engine performs better. Let's say the inverse. We get this thing on the dyno, we're going to start it straight up at 0, like that. And let's say that it's only peaking too low. It's not making enough power. The camshaft is a little bit too small. We need to put more cam in it. Well, loosen these 4 bolts and retard it back. That's going to delay the intake valve event. It's going to hold the intake valve open longer as the piston travels to the bottom of the cylinder, and it's going to allow more air to come in. General rule of thumb, if the camshaft is too small for the application, you can retard it to pick up some higher RPM power. If it's too big and you don't have any torque down low, you can advance it to pick up your torque numbers. So, it's the adjustability that a belt drive system like this gives us that makes it extremely advantageous in a new engine combination where we're going to tune the whole engine, not only with the EFI system, but mechanically tune the engine to optimize the best horsepower and torque numbers we can get. So, I'm going to start putting this system together on the front of this motor, and I'll walk you guys through that process. Okay, so step 1, we want to find top dead center of this engine so we can get the crankshaft in the correct position to put this system on. So let's bump this over with our bridge so we find TDC. Right there. So this piston is about 10 thousandths out of the hole. No problem. Alright, TDC is set. Let's roll the engine back upright. And I'm going to put a thin layer of RTV around this gasket. We always kind of joke here that our backup career path is cake decorating, because of how much we use RTV out of a gun. Okay, next we'll take our main backing plate. We'll pop it on the engine. Just like that. And we're going to go ahead and final install this rear plate to the motor. If you're really paying attention to what's going on, you'll notice that another really cool feature of this belt drive system is you can change the camshaft without removing the timing cover or the oil pan. Once this plate goes on, there's another seal that's going to seal this part of the engine. So if you want to change the camshaft, it's very, very easy to, and you don't have to take apart half the engine and change gaskets and create an oil leak and all that fun stuff. And I'm going to torque these to 10 pounds. Okay, next we have this bronze thrust washer. So we're going to put some assembly lubricant on it, and this will go up against the camshaft. Right there. Now we have this camshaft adapter that's going to bolt to the camshaft, and then that big upper billet gear will key onto it. So this guy now is just going to pop on here. And we will torque and final install this adapter. These only torque to 27 foot-pounds, so not a lot of stress. Next we have a second shim washer, thrust washer. So again, just a little bit of lubricant on this bad boy. Very thin layers on this stuff, guys. You don't need to go overkill. A little goes a long way. And next, we have the cam seal and retaining plate. So this plate now has a Teflon seal in it, and it's going to bolt right here and retain the camshaft in the engine block against the cover. Now, to set the thrust, we have 3 different shims of different thicknesses, because the camshaft needs to be able to move in and out just a little bit. It needs to have a little bit of thrust, just like the crankshaft does. And so we're going to start with all 3 of them to give us maximum clearance. We'll pop all 3 shims on. And now we'll slip this seal over the keyway and install it onto the timing cover. Very carefully not to damage that seal. And now I'm going to torque these to 9 pounds so the camshaft is locked in place, and then we can measure our camshaft thrust. I have a dial indicator on the nose of the camshaft, and I have it zeroed out. I'm now going to move the camshaft to the rear of the motor, and you can see we have 9 thousandths of thrust end play on the cam. Let's check it again, back to 0, back to 9. Jessel's spec is 8 to 12, so I'm going to go ahead and leave everything installed as it is because this is perfectly within spec. And we can carry on. The next step now is we're actually going to take this back off, and we're going to put some RTV on the back of these shims just to give us a little more insurance on any oil leaks.
Before we go any further, I want to recheck the cam thrust just so that we're 100% confident it's exactly right, because that is a very important measurement. If that measurement is off, you can see premature camshaft gear or distributor gear failure, which will send metal and debris through the entire oiling system. So I'm going to recheck it before we carry on. So let's go all the way forward with the cam. Really push it out there. Adjust our zero. And let's go back again. And we're about 10 thousandths. Again, Jessel's spec was 8 to 12. We've got 10 now that everything's final installed with the sealant and everything. So that's perfect with me. Next, we're going to install the lower crankshaft gear, or sprocket. And I'm going to put a little CMD on the crank, kind of as our anti-seize compound to help it slip on a little better. Here's that big sprocket. And we'll line him up like so. And I'm going to drive it onto the crankshaft. Now we need to put it together. So first, we're going to go ahead and lightly snug down these upper cam bolts with the camshaft straight up. So I'm on straight 0 degrees intake center line. And we've already rotated the engine to top dead center as well. So that's exactly where our alignment's going to be. Let's get this big belt. And they're not the easiest to slip on, but eventually you'll kind of figure out the secret to them. It's not the prettiest the first time, but there it goes, just like that. Kind of wrap that on there. And now we have our final washer. And this is actually a left-hand threaded bolt right here. So it tightens to the left and loosens to the right. And we'll torque this down to 70 foot-pounds. You know, everyone says you should never turn a torque wrench counterclockwise. Then how do you explain left-hand threaded fasteners? People, think a little bit. When you buy an $800 torque wrench like this, it comes with clockwise and counterclockwise calibration. Just saying.
Yeah, hold it. This is getting hard.
All right, there it is. Now that our camshaft bolt is torqued, we're going to set this straight up on 0 and final torque these camshaft plate fasteners to lock the cam gear into place. Now that everything's on the motor, you can see just how easy it is going to be for us to advance or retard the camshaft timing in relation to the crankshaft so that we can perfectly tune this engine's torque curve for the application. Now that the belt drive system is torqued and installed onto the engine, currently we have it set straight on 0, but Shay now is going to degree the camshaft in relation to the crankshaft so that we know 0 is 0, and if we want to add 2 degrees advance or maybe retard 3 degrees, we're actually doing that in relation to where the camshaft is supposed to be.
All right, guys, so we're set up here with the engine. I have a degree wheel and a dial bridge. And what I'm doing here is finding exact TDC, top dead center. So when the piston's at the very, very top of the bore here. So what I'm gonna do here is I'm gonna get it close, right? So that's pretty close to 0. And this is just a piece of welding wire. It really, you can use a coat hanger or whatever. So I have 0. I'm gonna actually roll the motor back. And what we do to find 0 is I'm gonna use an arbitrary number. So I like using 50. So I'm gonna go to 50 on this dial indicator here. And we're looking at about 10 degrees. And so I'm gonna go to TDC to go on the way back down, same direction of rotation, for that way you're not accounting for any slack in the chain, or in this case it's a belt and we don't have slack. But if you're doing this at home, you want to roll the engine the same direction every time. So we're going to come back down to 50 again, directly 10. So 10 before and 10 after. Right in the middle is 0. That's how we know the piston and the degree wheel are exactly in sync. So when this is on 0, the piston is perfectly on top. I'm going to throw a lifter in the engine, and I'm going to show you how to find center line of the intake lobe. So here's the cam card for this motor. Pretty large camshaft, as you can see here. 281 on the intake at 50, 296 on the exhaust. So pretty good size camshaft. 754 lift on the intake, 759 lift on the exhaust. So what I'm going to do here is follow the cam card. These specs are for cam installed at 112 degrees intake center line. 112 degrees intake center line, 112 degrees lobe separation. If those numbers are the same, there is no advance or retard ground into the camshaft. Sometimes you'll see intake center line is a 108 and the lobe separation is a 112. That means there would be 4 degrees advance ground into the camshaft. That's not the case here, so we are looking for 112 intake center line. I'm trying to get all of this in the frame so you can see what I'm doing here. Got quite the setup. So all I have is a lifter here with a push rod in a direct line. That way we get accurate measurements. If it's you know, canted off to the side, you're pushing at an angle, that's not going to give you an accurate measurement. So this is straight as possible. We're going to get it on the base circle of the cam, so not up on the opposite end of the lobe. And we're going to zero our gauge. So we're coming up here, as you can see. The lifter's going to go back down. Sometimes you have to help it along a little bit. So that's base circle of our camshaft right there. I'm going to move that to 0. Okay, at this point, I'm going to go 50 thousandths of 1 inch up on the lobe and compare that to our cam card. So as you can see here, our intake should open 29 degrees before TDC. So on this side. So let's see how close we are. Coming up. Right at 50 there. And let's take a look. Called for 29. As you can see, we are 29 on the dot. So that's just a testament to how accurate these Jessel belt drives are. Lining it up 0 right out of the box. Really no effort at all. And we are right where the cam manufacturer wants the camshaft in the motor. So that makes our job easier. I don't have to move it at all. Let me show you a couple ways to find intake center line. One way of checking it, intake center line, is we can go to the very peak of the lobe and then go an even distance. It's an arbitrary number, does not matter what number you choose to use. Like, here, let me just show you instead of trying to explain this. So there's the very peak of our lobe. So I can move that to 0. What I can do here, I'll move it back. And I will go, again, arbitrary number. I'm just going to use 30 before the peak. And I have about 77.5 degrees. We're gonna go to the peak of the lobe. We're gonna go back down to 70, the same number I used before, right there. And now I have 146.5. We get our calculator out. 77.5 plus 146.5 equals, divided by 2, 112. So that's one way to do it. I'm going to show you another way that will come in handy if there's an asymmetrical lobe on the camshaft. So that means the lobe is not exactly the same from one side of the lobe to the other. So let's get a visual on what having an asymmetrical cam lobe looks like. Your cam lobe, typically you think of shape like this. That's an example of a symmetrical lobe, meaning if we draw a line right down the middle, both sides are a mirror image of each other. Sometimes you can have a cam lobe that is very smooth on the ramp and then very aggressive on the other side, meaning you have a lot more area here than you do on this side. One side of the camshaft is more aggressive, opening or closing, than the opposite side. That makes it tricky using that method to find exact center line. So let me show you how to do it in that particular case. This is not applicable to 99% of any type of application. This is a very high-end race type situation here, but I'll go ahead and show you guys that anyway. So we're on the base circle of our camshaft here. As you can see, I've zeroed this indicator. We're going to go 50 up on the lobe. So roll it around till it goes 50 up. The cam card calls for 29 degrees opening at 50. So 50 up, 29 degrees on the dot. So I'm gonna write down 29 degrees on the table. We are going to count revolutions so we know how many revolutions up on the lobe it is, and we're gonna count them coming back down so we can stop right at 50 and get our closing number. There's 1, 2, 3, almost 4. There's 1, 2, 3, and we're gonna stop at 50 here. That's the 50 up on the back side of the lobe. Let me see if I can not go past it. Here we go. All right, 50 exactly. And I'm looking at 72 degrees after bottom dead center. So let me take you to the table over here. All right, let's see if you guys can see this. So 72 after bottom dead center. This is before top dead center. There is 180 degrees in between these two numbers. So you're going to account for 180 degrees that we didn't actually measure. So I know that may be confusing, but you're going to see the numbers are all going to come out correct. So what we're going to do are 180 plus our 72, you get 252. We're going to minus our opening number because that takes place on a, how do I explain this? So we have 29 before top dead center as our opening number. There's 180 degrees that we didn't actually measure, but we have to account for because the camshaft is in half time of the crankshaft. And then 72 after bottom dead center is our closing number. So what we're going to do is add 180 degrees that we didn't measure but have to account for, and 72 after bottom dead center. We get 252. We're going to subtract our opening number, so minus 29. That gives us 223 divided by 2, 111.5, within half a degree of what the cam card calls for. So as you can see, both methods work great. They get us within half a degree of what the cam card calls for. So whichever method you guys prefer to use to verify the numbers on your cam card, both work. Whichever makes more sense to you, go ahead and do it that way. Forgive some of the noise in the shop. We are trying to get stuff done while shooting videos.
Okay guys, as you have seen now, this Jessel belt drive system with our Smeding crankshaft and camshaft, the degree is perfect. We are within a half a degree, measuring it one way, and the other way we're dead on the money. So that's great for us because now we know that any change we make to this belt drive system to tune the torque curve of the engine is going to be accurate. In the next video, we're going to set up the valve springs on our cylinder heads, show you guys how we measured install height, and check the install pressure and the open pressure so that we can make sure the valve train is completely in sync and ready to operate. We're also going to mock up the cylinder heads on this engine and check piston to valve clearance, as well as measure push rods. Once we get the push rods on order, we can then final assemble this bad boy and get it on the dyno. See you guys then.